Savart Law. Savart Law tells us about the magnetic field produced around a current carrying a small element. But before we go into detail of this particular section, we will study first of all how the moving charges produce magnetic field around them. First of all, we are going to study this only, magnetic field due to a moving charge. Suppose a charge Q is having the velocity v. Then at a particular point, the magnetic field produced by it will be given by a relation. So let's know first of all that whenever the charge moves, charge in motion, then it will certainly produce magnetic field around it, all the sides. That field is given by this relation mu naught upon 4 pi q v cross r upon r q. If you write in vector form, this is going to be r cube, and if you just divide this vector form, you will get the relation mu naught upon 4 pi q v sine theta upon r square. Mu naught, you know, that is permeability of free space. Its value is 4 pi into 10 to the power minus 7 Newton per ampere square. Then, on the basis of this magnetic field produced by a moving charge around it, we can find how two moving charges will produce a force on each other. You already know whenever there are two charges, maybe both are similar, both are opposite, in all the cases there will definitely electrical force between them. Whenever there are two charges, you know they apply electrical force on them. But now here going to add, whenever charges move along with this electrical force, there will be magnetic force between them. That we'll find out here. You see, we have checked the nature of the charges. If both are positive, this force is going, electrical force, going to be repulsion. Both are positive, repulsion. Opposite means one positive, one negative, electrical force will be attraction. First of all, I have clarified how the electrical force will be decided, that we already know. Now, what is the idea of finding the direction of magnetic field? Suppose the charge is going this way and you want to find the field at this particular point. Then for that, you see, you have to follow right hand curl rule. Listen again, right hand curl. Curl means to rotate, C-U-R-L. Right hand curl rule. What does it say? You put your thumb of your right hand in the direction of the current. Then these rotating fingers, you curl your right hand. These fingers will give the direction of magnetic field. For example, you choose this point. You choose a point over here. Current is this way. Current is along the thumb. Then here the magnetic field will be vertically downward. And this point, you are choosing the point over here. See, here the field will be towards B. And if you choose the point over here, exactly in the front of this wire, then again thumb in the direction of current, and this will be vertically upward. So all around you are going to get the direction of magnetic field with the help of curling of right hand. It's very interesting, this field comes out to be in the form of concentric circles. Why concentric? Because the ultimately center for all the circles is going to be on the wire itself. Then on the basis of that, you are having two charges, and both are having the velocity v1, v2 in the same direction. You see, with the help of first one, this wire, the field at the second wire is going to be normally inward with the help of right hand curl rule. Here the field produced by this will be B1, that is normally inward. And when this field is normally inward, you apply Fleming's left-hand rule. This is magnetic field, this is current, this will be the force. Field is here, normally inward, and the current or the velocity of the charge is this way along plus y-axis. You see the force is going to be towards the first charge. That is what we call attraction. So one very important result is that whenever two similar charges are moving in the same direction, they will have the force of attraction. That's what I have shown over here. Two similar charges moving in the same direction, they are having attraction. Obviously, if we change any one of these 4 points, this nature will change, because you see I have reversed the direction of velocity, so the force becomes repulsive, and so on. Again, I have changed this sign of charges, again this force will change, but here also I have changed the direction. It was opposite, now they are in the same direction. Two changes have occurred in this row, that's why it's not going to be affected. And likewise, you can have this result. Different possible cases have been shown over here. Then we'll consider basically what is called Biot-Savart law. This name was given for a current element. When there is a small current element of length L, it's shown over here, dl. You want to find the magnetic field at a distance having vector r, its location vector r, and current flowing is I. In that case, the magnetic field is going to be mu naught upon 4 pi I dl cross r upon r cube. dl cross r, this will be r upon r cube. And if you are interested, you don't want to write this in vector form, you could write it as mu naught upon 4 pi I. This r, you see, if you remove the vector form, it's going to be r square only. Then I dl sine theta upon r square. This is the value of magnetic field in which we haven't used the vector form. Here I have given the value of permeability of free space 4 pi into 10 to the power minus 7 Newton per ampere square.